Hello everyone, this is Hao Zheng. Today, I'm delighted to share with you our recent work on network monitoring. This is a project from Nanjing University. Firstly, let me provide some background information. Network monitoring systems are widely deployed and play an important role in network management. In general, a network monitoring system serves two primary purposes. The first is application traffic measurement. We can utilize traffic monitoring tools to gather traffic-related metrics such as flow counters, flow completion times. The second is to monitor network events or status. Network operators need to access the status of network devices, such as congestions and packet losses. Today, our topic is about the time granularity of the network monitoring. For application traffic measurement, the time granularity refers to the size of the counting window. A coarse grain time window means each counter covering packets over a long time span. On the other hand, fine grain time granularity means shorter or small windows. In the context of network event monitoring, the time granularity means the frequency of reading network status. Fine-grained observation implies more frequent reading of network status. Okay, here is the problem. There is a gap between monitoring time granularity and activities in data center networks. Modern data center networks now have ultra-low latency measured in the microsecond time scale. This is achieved thanks to many advanced techniques such as RDMA and faster network devices. With these techniques, the flow behaviors and congestion events now occur at the microsecond time scale too. However, current monitoring systems operate at only millisecond to minute level, missing a lot of valuable information. There are two cases. In current high-performance networks, when congestion occurs, congestion notification packets return to the sender at the microsecond level. This means that change in the flow rates occurs at the microsecond level. It brings up a question. For hardware and software stacks that may have some performance issues, how can we find the root cause? If we conduct the experiments in a simulation environment, the problem is easy to solve because we can print all information at any time scales. However, the actual production networks is not like that. We only have coarse-grained monitoring tools. As shown in the figure, these tools can only give the average rates. Developers cannot get enough information to analyze the performance issues. Another case is on queue monitoring. In current networks, microbursts occur frequently. Existing work shows that 90% of microbursts last less than 200 microseconds at 3 types of workloads. The current coarse-grained monitoring can easily miss some microbursts between polling intervals. On the surface, it seems that there is no congestion events. In fact, there are many microbursts. So our observation is that microsecond level monitoring is urgent for analyzing today's high-performance networks. There are some related works in this field. The first is traditional monitors. They operate at seconds to minutes level. The second is recent monitoring systems such as Trumpet, Florida, and Sketches. They operate at millisecond level. Existing microsecond level monitoring systems can be divided into traffic measurement system and network event detection systems. For traffic measurement purpose, existing systems operate at interface granularity or at packet granularity. The interface granularity cannot observe per flow behavior, and the packet granularity limits the large-scale deployment. As for detecting network events, existing fine-grained solutions rely on programmable switches. To conclude, there is no network monitoring system that simultaneously supports microsecond-level flow rate measurements at scale and congestion analysis on commanded switches. It's not easy to achieve the microsecond-level monitoring. Here are 3 challenges. The first challenge is the increase in the amount of measurement data. For example, if we refine 10 millisecond granularity to a 10 microsecond granularity, in the worst case, each counter needs to be expanded to 1,000 counters. We also evaluate 2 typical workloads. We found the amount of data will increase by dozens to hundreds of times. This put a lot of pressure on device memory and bandwidth. The second challenge is how to detect and analyze congestion events. To achieve large-scale deployments, we need to consider a general solution that can work directly on legacy commodity switches. Consider the potential resource cost of the new functions. The short challenge is how to distribute microsecond-level measurement functions among network devices. We design and implement micromon, and this page gives a high-level view of the system design. The system consists of three parts. The first part is microflow measuring at end hosts, where we measure the microsecond-level rate information of each flow in a lightweight and accurate way. The second part is micro-event detection, where we capture congestion events on commodity switches. The third part is an analyzer. In the analyzer, we collect microflow rate information to perform fine-grained traffic analysis. We also collect congestion event packets captured in the network, which mark the time, location, and related flows of the congestion. Based on this information, we can understand the real-time network load status at the microsecond level. More importantly, if we are interested in a serious congestion, network operators can replay the congestion events by plotting the rate variations of the associated flows near the event occurrence. In summary, micromon's analyzer supports three main functions: microsecond-level flow analysis, congestion detection, and the replay of the congestion. Here are some details of the microsecond-level flow measurement. Review the target. We need to count the number of packets or bytes of each flow in consecutive time windows. The key question is that how to compress the counter sequence to reduce the memory or bandwidth costs. We can consider two strawman solutions. The first is to use traditional compression tools. However, these tools often require complex computation and memory operations that are not suitable for data plan implementation. So we first need to transfer the uncompressed data to the control plane through PCIe channels, which is unacceptable since the data volume is large. The second strawman solution is to directly use sketches. However, existing algorithms destroy the continuity of the counter sequence. In microsecond-level monitoring, they cannot effectively compress the counter sequence and will bring unexpected noises. So, there are two requirements for an ideal solution. The first is that we need a compress on measure algorithm, which means we need to directly compress the measurement data in the data plane without transferring the uncompressed data to any other places. The second is that we need to keep the drastic changes and overall trend of the counter sequence without introducing noises. Micromon's answer to this problem is wavelets. The key idea is to abstract the counter sequence as waveforms and then compress them using wavelet transform theory. Here is a rate curve view of the counter sequence. Wavelet transform compress the waveform of this curve in three steps. The first step is wavelet transform. The original rate curve is decomposed into a set of wavelet functions of different scales and positions. In wavelet transform theory, each wavelet function is derived from a mother function through scaling and translation. It can effectively decompose the original curve so we can analyze which parts are important and which parts are relatively smooth and can be ignored. Based on the transformation, the second step is compression. We can filter out the wavelet functions with least influence on the flow rate curve. Finally, the third step reconstructs the rate curve from incomplete wavelets with some accuracy losses. Here is a practical example to show the process of wavelet-based compression. As we can see, the transformation is a multi-level process. There are L1, L2, and L3. Each level operates on a different scale, covering different range of counters. In the compression stage, we make a selection on those multi-scale wavelet coefficients. The reconstruction stage is an inverse process of the transformation, and it reconstructs the curve from the coefficients. During this process, the most important advantage of wavelet-based compression is called multi-resolution analysis. When compressing the data, we can automatically capture the components that best characterize the curve from different time points and different scales, and discard those minor components. However, to apply wavelet transform to network measurement, there are three problems need to be solved. The first is that we need to simplify the calculation of coefficients. The second is we need to give a strategy for coefficient selection in the compression stage. The third is that we need to adapt the process to an online and streaming fashion to meet the performance requirements of network measurement. We introduce WaveSketch to solve the above three problems. WaveSketch is built upon a counting sketch with several rows of buckets. The difference is that each bucket is no longer a simple counter, but some variables used for wavelet transform. WaveSketch updates each bucket as follows. Firstly, a counting stage counts packets within a time window. When a new window arrives, the old counter will go into the transformation stage. In the transformation stage, we use several methods to simplify the wavelet calculation. We use higher wavelets as the model function. In higher wavelets, we can only use simple addition and subtraction operations to complete the calculation of the wavelet coefficients. The transformation stage will generate some wavelet coefficients. The compression stage is to select the top k coefficients with a weight. The weight is used to reduce the reconstruction error. The last is the reconstruction stage, which is only performed in the micromon analyzer. The WaveSketch has some good features. Firstly, it is an algorithm with O1 update complexity. Second, it has good compression performance with little reconstruction errors. We discussed the update complexity, compression ratio, and hardware implementation of the algorithm in our paper. Please see the paper for more details. This page gives several application examples of WaveSketch. When query a WaveSketch, we need to input flow ID and time range. The flow ID is required to locate specific buckets. The time range are used to select the range of the rate curve in these buckets. Microsecond-level flow rates can be used for in-depth analysis of flow behaviors. For example, we can observe the behavior of a low-rate flow. In this figure, the flow is full of transmitting gaps. We can judge that the flow cannot continuously provide sufficient data to the link. This indicates that the poor performance may be caused by high-latency network stacks. Another example shows some different points. We can observe the behavior of multiple flows in the same time period to confirm whether the congestion control protocol is working correctly. Unlike the previous low-rate flow, this RDMA flow is sent continuously. However, due to the computation of another on-off flow, its rate is oscillating. Through WaveSketch, we can observe how the RDM flow responds to congestion and how the rate recovers after the congestion disappears, thereby verifying the transport algorithm. Another important use case is congestion event replay. The first step is to capture the congestion events and identify the flows during the congestion. So the question here is how to detect congestions and related flows. A simple solution is used in micromon for ease of deployment. We match and measure the CE marked packets. These event packets carry the flow information and timestamps. With WaveSketch, we can replace the event by querying the rate variation of the related flows. To mitigate the bandwidth overhead caused by duplicate packets of elephant flows, we also perform a sampling strategy. The above functions can be implemented with common features available in commodity switches. Many existing well-designed solutions can realize more accurate congestion detection and more efficient packet deduplication with programmable switches. And micromon is also compatible with these solutions when programmable switches are available. Here we give some evaluation results on two aspects. The first aspect is the evaluation on microflow measurements. The time granularity is set about 8 microseconds. The baseline methods include persist sketch, average version of mMON, and Fourier transform-based compression. Below is the evaluation results. In the 15-load Hadoop workload, WaveSketch improves accuracy by 3.5 to 57 times. This is the average result of the whole workload. If we zoom in to observe a specific flow, we find that the wavelet-based approach can use memory to preserve the most important part of the curve, while using this memory for the relatively smooth part. The second aspect of the evaluation is on the congestion detection. We use fat-train topology and run Hadoop and web search workloads at different loads. We evaluate congestion recall ratio, flow recall ratio, and bandwidth cost on various sampling rates. We found micromon can capture 99% of congestions that exceed the Kmax threshold with a sampling probability of 1/64. It costs about 31 to 82 Mbps bandwidth cost per switch, and 50 to 73 flows are captured. Finally, let me make a conclusion. microMON is a novel microsecond-level network monitoring system for data center networks. We focus on two main functions that empowering microsecond-level monitoring. The first is microsecond-level flow measurements. The second is microsecond-level congestion analysis. For future works, we will try to promote large-scale deployment in production networks, and we will explore the algorithm design for higher accuracy and better performance. This concludes my entire presentation. Thanks for your listening.